Welcome to Lecture 1.2, Spanning, Independence, and Bases. We previously introduced the notion of a vector space, and this consists of a set X of vectors, a set F of scalars. We use F because it's a field. We can add, subtract, multiply, and divide. And then X, the space, is closed under addition, subtraction, and scalar multiplication. Though we don't really need subtraction, because when we have scalar multiplication, given a vector, we can get its negative, multiply by -1, and then just add that to something else. And then, of course, it's equipped with the natural associative and distributive laws that we normally take for granted. We saw how linear maps are structure-preserving functions between vector spaces. And finally, we learned about special subsets of vector spaces that are also vector spaces, and those are called subspaces. In this lecture, we will look at subsets that are not necessarily subspaces. Often they are finite sets. And we will learn what it means for them to be spanning. You should think of the word spanning as generates X. Linearly independent, which you can think of as having no redundancies or no extra unnecessary vectors. And a basis, which means it's both of these. So it's large enough to generate, but small enough to not be redundant. Finally, we will also formalize what the dimension of a vector space really is. Let's start with a few definitions. First of all, a linear combination of vectors x1 up to xk is just a sum of these vectors with coefficients in front. So that is a vector of the form a1 x1 plus ... ak xk, where each ai is in the field k. Next, given a subset S of vectors, the subspace spanned by S is the set of all linear combinations of vectors in S. And we denote this as the span of S. Now I should mention that we are only allowing finite linear combinations, so S could be infinite. It could be like half of a line or half of a plane, but we are only allowing sums of finitely many terms at a time. It's a worthwhile exercise that I usually leave as homework, that for any subset of vectors, their span is equal to the intersection of all subspaces that contain S. Now sometimes for notation, we will shorten this to be y alpha. So we might use a less than or equal to sign to denote subspace. That's inspired by how that sign is used in group theory to denote subgroup. And then we write something like that. So this is just another way to write it, but here I wanted to emphasize what's meant by that by spelling it out. Now this is a common theme in a lot of areas of mathematics, that there are two ways to build a certain type of object. On the left is from the ground up. It's saying, let's take the individual elements and let's add them together in every possible way. Take all possible linear combinations. So that's sort of from the ground up, whereas the right-hand side says, let's take everything bigger than S, that is that type of object, a subspace, and let's intersect them all. And this is sort of from the top down. So it's a little bit of a picture. So suppose S is this set like this, could be finite or infinite. The left-hand side is taking all possible combinations of this, where the right-hand side we are taking all possible subspaces. And this is a cartoon. Subspaces don't look like this. And we are intersecting them, and then what we get is the intersection of all of these things is the actual span of the subspace itself. Now, anytime that you have two sets like this that are equal, like if you have to show that A is equal to B, the way to do this is to show two containments. First of all, that A is contained in B and that B is contained in A. And this really means usually it means take an element in A and show it's in B. And similarly, take an element that's in B and show it's in A for this containment. Now that's how this is going to work in one direction. So I'm not going to do this, but I'll talk about how this goes. So to show this containment, that the span is contained in here, you take an arbitrary element in the span. So we know what that looks like. It looks like this. And since each individual xi, or I think if I were writing a proof, I would call these si's. Since each of these is in every single y alpha, then this linear combination is in every single y alpha. And so if this linear combination is in every y alpha, then by definition, it is in the intersection. So that's how this goes. You just argue element-wise, classically. But the right-hand side, we can't really do it for the other direction. So if we're trying to show this direction, because we don't really know what an element in the right-hand side looks like. Like, what is a generating set? We don't really know. However, what we can say is we can do a more set theoretic argument. And this is the sort of thing that if you don't see it, you don't see it. You have to work at it, think about it, and at some point it'll click and you'll have this aha moment. I've seen it, trust me, many times. So I'm going to again draw a cartoon for intuition. So suppose that this is y1, suppose this is y2. Now these there does not have to be a finite or countable number of these things. So again, I'm just trying to illustrate this with a picture. Don't take it too literally. And so maybe this is y3. Now these are all subspaces that contain S, which is this set. Could be finite, could be infinite. This is a set of all subspaces. Now this guy on the left, this is a subspace that contains S. So it is one of these y alphas. So let me call this, I don't know, let's call this like y, 18 equals span of S. So it is a general rule of set theory. So let's pause for a moment and say it's a general rule of set theory to notice that if you have a collection of sets, say this is like y1, y2, y3, and y4, that the intersection of these sets, yi, is absolutely contained in any individual one. So the intersection is contained in y2 or y3, right? Because the intersection is this little piece right here. It's contained in every single one of them. And that's what we have down here. We have an intersection of a whole bunch of subspaces, which is contained in this one individual subspace. So this is using a set theoretic argument, you can get the other direction. Now I said that this comes up in a lot of areas of math. And so for example, given a subgroup. So in group theory, you don't have to know what a group is, but given a subgroup generated by a set S, that is also equal to the set of all subgroups of G that contain S. So let me call those H alphas. And there's a lot of examples of this as well in group theory, ring theory, and other areas. Now you've got to be careful because sometimes the intersection of a whole bunch of things does not have that property. So if you intersect a whole bunch of closed sets, you may or may not get a closed set. So you can try to do something like this for normal subgroups, but if you intersect a bunch of normal subgroups, you may or may not get something that's normal. But this example, I think we will see problems like this later in the class where a different type of object can be built from the ground up or from bottom up or top down. Another example I think is the convex hull of a collection of points. So this is something that comes up in discrete geometry course or combinatorics class. And I know I'm going a little bit of a tangent, but I think it's worth mentioning this. So the convex hull of a bunch of points, you can intuitively think about as if these things, this could be in any number of dimensions. Let's just do it in 2 dimensions. It's what you get by thinking of these things as nails and you are stretching a rubber band around them. And so, if you do that, it looks like this. Now, there are multiple ways to define this. I think the 2 most common ways, I missed a point here. One of them is by looking at all convex combinations of these points. And so really, without defining it formally, what that is so this point is halfway between these two. this point here you can write as using these two and maybe this third one as well. So it's in the interior of this. So this is sort of doing it from the ground up. And the other way you can define these things are as the intersection of all half spaces that include the set of points. So everything on this side of this line is a half space that includes all of these points. Everything on this side again. So all of these are half spaces. And of course, if you do this, the ones that really matter are the ones that bound this region. And so if you take everything that is in this, so everything, I don't know how to draw this too, everything that's under this line, that's to the left of this line, that's above this line. So instead of points, you just define it as the intersection of of infinitely many half spaces. And this works in any number of dimensions. Again, imagine in 3 dimensions, you got a bunch of points, and then instead of taking a rubber band around these, you are taking, I don't know, like a balloon and a rubber and stretching it to get a solid. And you can define those as the intersection of hyperplanes instead of half spaces. Finally, our second main definition is that of linear dependence and independence. So the vectors x1 up to xk are linearly dependent if we can write them as a linear combination to get the zero vector where not all of the coefficients are equal to 0. If they're not linearly dependent, they are linearly independent. Now sometimes I'll just be saying dependent or independent, because though there are other forms of dependencies like algebraically dependent, we're not going to be talking about those, so it should always be clear from the context what I mean by dependent or independent. Let's start with a lemma. If a vector space X is spanned by n vectors, x1 up to xn, and the vectors y1 up to yk are linearly independent, then k has to be less than or equal to n. So let's prove this. So what we'll do is we will take y1 and write our first vector as a linear combination of the xi's, which we know we can do. So a1 x1 plus ... a n xn. Now, we know that not all of these are equal to 0. Well, I should mention, I don't need to write it down because it should be clear that all of these yi's have to be non-zero. Because if any of these are 0, then we have a non-trivial way to write the 0 vector, just 1 times that vector. So y1 is non-zero. We are writing it as a linear combination, and not all of these coefficients are going to be 0. So it doesn't matter which one we say is non-zero. So we will write that without loss of generality, that a1 is non-zero. Otherwise, we could just renumber. So because of that, we isolate and solve for x1 because we can divide by a1. So in other words, we can write x1 equals 1 over a1 y1 minus, making sure I'm doing this correctly, a2 over a1 x2 minus ... a n over a1 xn. So we can basically solve for y1, and then we can just eliminate it because we can stick it right in here for x1 and say then the span of x1, x2, all the way up to xn is equal to the span of y1, x2, all the way up to xn. Because if we take this creature and put it in for x1, now we can generate the entire vector space, but we are not using x1 at all. We are using all of these guys. So we are using y1, and then x2 up to xn. So we have basically eliminated x1 from here, and then we can keep going. So next, we can write x2. Now we got to be careful. We don't want to write x2 as as using x1 up to xn, because then we might reintroduce an x1 if we sub back in. So we want to write x2 using our new basis. So write x2 as b1 y1 plus b2 x2 plus ... bn xn, and then that is what we want to solve. We want to eliminate x2 from it. So let me call, I guess this is x, then x is equal to the span of y1, y2, x3, all the way up to xn. So we can repeat this process. And I claim that we will eventually run out of the yi's before we run out of the xi's. Okay, so let's write this down. I claim that k has to, or that, how do I want to say it? K bigger than n is impossible. And let's think about why. So, because if not, then what we would have is we would have the very last vector being unused. So then yk would be in the span of some of the yi's. So let's write y1. There's nothing wrong with being generous and throwing in all the way up to yk minus 1, which is x. And if that were the case, then that means that we could write yk as a linear combination of these guys. So that means that we could write yk as c1 y1 plus ... ck minus 1 yk minus 1. And if we did this, then we could move the yk over to the right-hand side, and we would have a non-trivial way to write the zero vector. And this is impossible because the yi's are independent. Okay, so that's the end of the proof. Now we come to the definition of a basis. There's not much to say other than a set B is a basis of X if it spans X, so it's big enough to generate, and it's linearly independent, so it's not too big. As an exercise, something I recommend doing, the following are equivalent conditions for a subset of X. So the first one is that B is a basis of X. That is equivalent to B being a minimal spanning set of X. And finally, B is a maximal linearly independent set. So I want to emphasize these words minimal and maximal, what they mean and why they are different from minimum and maximum. So B being a minimal spanning set means it spans, but it's minimal in the sense that if we remove any vector from B, we lose that property. It no longer spans. Similarly, B is linearly independent, but it's big enough that if we add anything to B, we destroy that property. Now, I like coming back to the field of group theory, even though not everybody is familiar with it. I think some of the basic objects are accessible enough. So if you look at the set of all permutations, let me look at 5 elements. So suppose you have 5 chairs and you have people sitting in those chairs, and you want to get all seating arrangements. How do you do that? Well, you can have people in the first 2 chairs swap seats. So we'll call that 1, 2. We can have people in the second and the third chairs swap seats. We call that 2, 3. People in the third and the fourth chair swapping seats, we'll call that 3, 4. And the people in the fourth and the fifth chairs swapping seats, we'll call that 4, 5. So the set of permutations of 5 elements, we write Sn don't worry about the notation, for the symmetric group, it is generated by these 4 permutations. So 1, 2, 2, 3, 3, 4, and 4, 5. So that's one way to generate all permutations, and it's clearly a minimal way to generate it, because if you remove one of these permutations, you can no longer get all permutations. So for example, if you don't let people swap seats in the first and the second seat, then you have this, and then the person in the chair 1 can never move over to the right-hand chairs, and so you don't get all the permutations. Now, another way to generate these permutations is instead just allow this first swap, 1, 2, but also allow people to cyclically shift. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes back to 1. So we write that as 1, 2, 3, 4, 5, and those things will generate all permutations as well. Now, this is also clearly minimal, because if you remove one of these, you break that property, but here you have 2 different generating sets that are both minimal, but they are different sizes. So we don't want to say minimum for multiple reasons. First of all, there are smaller sets than this that do the job, but also there is not one and only one smallest set like a minimum, like in calculus, a global minimum or local minimum might suggest. Now, I'm not going to prove this. I encourage you to try it yourself. And of course, to prove something like this, you need to show that 1 implies 2, 2 implies 3, and 3 implies 1. And that's not the only way. You can go backwards. You can say 1 implies 3, 3 implies 2, 2 implies 1, or you can even show these 2 are equivalent and these 2 are equivalent. But you really should be able to, given one of these, show that any other one is true as well. Although some of the steps are easier than others. Okay, let's do some examples. So let's take some of our familiar vector spaces and talk about bases. So Kn is the set of all n tuples. And so a basis for this is going to be, I'm just going to write it as E1, E2, En, where Ei is the vector of all zeros, and this is position I. So that's one basis of many. There's many other ones that you could use. We're not going to get into how to test whether something is a basis. That's actually something you probably learned in your undergraduate linear algebra course. So if you have there's a matrix you can construct, and that matrix has to have full rank. But here we're more interested just in the theory behind the scenes. So next, the set of functions from a finite set. So similarly, we can think of so suppose S is set S1 up to Sn. So one basis is, you can call these characteristic functions. So chi of, let's say chi I of Sj equals 0 if I is different than j, and 1 if I is equal to j. So there are n of these functions, and those will form a basis. Again, not the only basis. And then finally, the set of polynomials of degree less than n with coefficients from k. Again, there's many ways to form basis. The canonical one is to take 1x squared all the way up to x to the n minus 1. Now, sometimes I'm a little sloppy with notation. Sometimes I let a basis be a set. Other times I just call it a list, or I might just write the set of chi i's, and maybe I'll say I equals 1 up to n. I don't think it matters too much whether you use set notation or just list the vectors. Okay, next in line is another very straightforward lemma. If a vector space is spanned by n vectors, x1 up to xn, then some subset of that is a basis. So we never have to worry. We can just keep removing vectors blindly until we wind up with a set that is linearly independent. So to prove this, first of all, note that if x1 up to xn is independent, so I'm just going to write independent, that means linearly independent, then we are done. So if not, then let's think about what that means. Then that means that we can write a1 x1 plus a2 x2 plus all the way up to an xn being 0 in some non-trivial way. So not all of the an's are 0. So we can say without loss of generality that an is non-zero. So if we do that, that means that we can solve for xn, and we can write xn equals something times x1 plus something times x2 plus something times xn minus 1. So we can call these things something else like b1, b2, and bn minus 1. So I don't think you need to include this in the proof. This is something that I would assume that the reader can figure out. So we can say, if not, then we can write without loss of generality xn to be b1 x1 plus bn minus 1 x to the n minus 1. So now in this case, span, now we can plug these guys back in for xn and eliminate xn and get that the span of the first n minus 1 vectors is equal to x. So just repeat this process. And eventually we will get a linearly independent set. And it will take finitely many steps because we have finitely many vectors. And eventually the remaining, I don't really think I need to say this, set is independent. And that's that. A very simple definition. A vector space is finite dimensional if it has a finite basis. And you may be saying, well, don't all bases have the same size? Yes, but we have not shown that. And we just saw an example in group theory and permutations where a basis or a minimal generating set does not have the same size. But no, that's not a vector space, but that's why we should always be cautious when things that we want to be true are not always true in every context. So a few examples in Rn. One vector in an n-dimensional space is linearly independent if and only if it is non-zero. Two vectors are linearly independent if and only if they do not lie on the same line. In other words, they are not scalar multiples of each other. And three vectors in Rn are linearly independent if and only if they do not lie on the same plane. Next up, let's state and prove what I just said that we knew to be true, which was that all bases for a finite dimensional vector space have the same cardinality, which is what we call the dimension of the space. So to prove this, let's let b x be one basis, say x1 up to xn. And let me call the other one by, y1 up to ym, be bases. Now, bx spans x, and by is linearly independent. So we proved earlier that that means that m is less than or equal to n. Now similarly, by spans x, we just exchange the roles, and bx is linearly independent, so we can conclude that n must be less than or equal to m, and that completes the proof. The next result is both very straightforward, but also surprisingly useful as a technique. This is, if we have a linear independent set of vectors, say y1 up to yk, in a finite dimensional space, then we can always extend that to a basis of x. So we never have to worry about backing ourselves into a corner and having to remove vectors and add them a different way. We could just greedily add vectors one by one until our set spans. So let's write that down. So this says that, so we're saying that if the span of y1 up to yk is not equal to x, then find yk plus 1 that is not in the span. And then repeat. And then include it. So next, if the span of y1 up to yk plus 1 is not equal to x, then find some yk plus 2, which is not in that span, y1 up to yk plus 1, and include it. And then so forth. So this process will terminate in how many steps? In, well, less than or equal to the dimension of x steps. You can get better than this, actually, if you look at the difference of the dimension of x and k. But all we need is that it terminates, because otherwise it would contain more than n linearly independent vectors. We already know that the number of linearly independent vectors cannot be any more than the dimension of the space itself. And that's the proof. I want to finish this lecture with an example from differential equations. Now, even if you aren't familiar with ODEs, I think this example is straightforward enough that you can still follow it. So let's let x be the set of all smooth functions, x of t, so we've got infinitely many derivatives, that satisfy the second order differential equation x double prime plus x equals 0. So another way to think of this is that, so as I said, x double prime plus x equals 0. That's one way to think of it. You can also think of it using this operator as d squared dt squared plus 1 applied to x equals 0. So this is literally the set of functions that are sent to 0 by this differential operator. If you remember your undergrad linear algebra course, this is in the kernel or the null space of this differential operator. So it's easy to show that if x1 and x2 are solutions to this, then so are their sum, and so really are any linear combination of them. So the solution, we say the solution space to this, or the general solution, is a vector space. And this is a fundamental result of in differential equations, that if you have an nth order equation like this, basically an nth order equation which is some linear operator times x being 0, the 0's got to be on the right hand side, then the solution space is an n-dimensional vector space. So even if there's variables in here, even if it's like x triple prime plus t squared x double prime plus e to the t x prime plus 2x equals 0, that can be written as d cubed over d3 cubed plus t squared d squared over dt. I should have given a simpler example, plus e to the t d dt plus 2. This differential operator applied to a function equals 0. The solutions are the null space, the things that are killed by this differential operator. Okay, so in this case, solutions describe the motion of a mass spring system, so simple harmonic motion. And a particular solution is determined completely by specifying the initial position and the initial velocity. So think about if you have a mass spring system like this. So here's your mass. If you specify the initial, how far you pull this thing down, so maybe you pull this down to here initially, and then maybe you also have to specify whether you are letting it go or if you're pushing it up or pushing it down. That's your initial velocity. But once you specify displacement of velocity, then the motion is determined for all time t. So in other words, we can describe an element in the solution space by a pair of initial displacement and initial velocity, where these are real numbers, or more generally, the math usually ends up being nicer if we allow them to be complex numbers. So this defines an isomorphism from this solution space, the general solution, to C2 that sends any function to the ordered pair, initial position and initial velocity. Note that by inspection, sine and cosine are two independent solutions. If you think of this, what this is really saying is find all functions whose second derivative are equal to their negative, and you know that sine and cosine both satisfy those properties. And since the solution space is two-dimensional, then the general solution is just a cosine of x plus b sine of x, where a and b are arbitrary numbers. So you can really think of this as like your v1 and this is your v2. But of course, these are functions. Said differently, sine and cosine together form a basis for the solution space of this ODE. Now, it's not the only solution space, of course. If you take cosine of x plus I sine of x, you get e to the ix from Euler's formula. And cosine of x minus I sine of x is e to the minus sine of x. So these are linearly independent functions because there's only two of them and they are not scalars of each other. Therefore, they also form a basis. Way you can think about this is your solution space is like this two-dimensional space, and well, here's your sine and cosine functions, but hey, here are two other functions that also are on that two-dimensional space, so they form a basis as well. So the general solution, if you want, can be written as C1 e to the ix plus C2 e to the minus x instead. Now, this has some advantages and disadvantages. You can't graph these functions nicely. Now, this is why I said the complex numbers instead of the real numbers, because I knew these were coming. But sometimes these are arguably more concise than these things, especially if you are dealing with Fourier series. So in an ODE's course, you usually learn about a way to solve equations like this, and you get this first, and then we say, well, we don't really want these. We'd rather write them as sine and cosine, so you do some cute little algebraic manipulation to get that. But really, the reason why is because the solution space is a 2D vector space, and all you got to do is find any two functions that are not scalars, and there's your basis. So if you wanted to, you could use cosine and e to the negative ix, but I don't know why you would ever want to do that. Okay, so next lecture, we will talk about how to multiply vector spaces together, so how to take direct sums and direct products. And then after that, we will conclude this section with how to divide vector spaces by their subspaces and to get a quotient.